Good morning everyone. Today we are going to see RTL design using verilog HDL for beginners. We have levels of abstractions in verilog. We can use the modeling types as per the behaviors of the circuit. We have levels of abstractions, switch level modeling, gate level modeling, structural modeling, data flow modeling, behavioral modeling, and we will be seeing today's in data types, operator, task, functions and finite state machines. The reference books for verilog is Douglas J. Smith, Publisher Down Publication, and Verilog HDL Primer 3rd edition, J. Bhaskar, and the Guide to Digital Design and Synthesis by Samir Palnitkar, 2nd edition. In this module, we will be learning about the design specification of a digital circuit using different modeling styles, explain the design of test benches, explain the system modeling with task and function, simulation of digital circuits. Here is the introduction to Verilog. ASIC design flow, ASIC application specific integrator circuit. It starts with RTL design, next RTL verification, synthesis, physical design. MRD, market need. As per the market requirement, it is developed. Initially, the design specification is given. The next, architectural definition, microarchitecture definition. Next, RTL design, register transfer level designing using any languages, Verilog, system Verilog, VHDL, any languages can be used. Finally, it will be under verification. If it meets the code, the next process, the synthesis, logic synthesis will be done, DFT, design for testability. Next, layout versus schematic, netlist. Netlist is nothing but interconnections and gates what we are using. Next, the pre-layout STA, static timing analysis. Timing analysis, if it is meet, the synthesis is done. If not meet, again the same process of RTL design will be carried out. Next comes the physical design. Application here, placement and routing. Automatic placement and routing application starts here. Next, LEC. Layout is done, extraction is done, parasitic extraction is nothing but RLC. Here, if the timing goals meet, physical verification will be done. If not, again the same process will be continued for placement and routing. Next, OPC, design for manufacturability, and optically it is done. Finally, the tape out is done for a chip. Traditional IC design flow starts with, for example, we have taken a full adder. The truth table is considered, a K-map is done, a simplified version of a logic circuit, and it is constructed using a physical design mask layout, and then it goes to tape out and foundry. Finally, the chip is done. Here it is a basic IC design flow. Next, the solution. We need a specification. If not feasible for large design, we have a truth table. Next, we have a good idea is hardware description. Every time we need a hardware description in order to establish a chip. So RTL code. Next, a simulator. If it is bug free, we will be using a synthesis tool. And finally, hardware and netlist is created. Netlist is nothing but interconnection and gates what we are using for the chips. Here is the introduction for hardware description language, HDL. Programming language used to capture the structure, functionality and data flow of electronic circuits. We have Verilog and HDL. Verilog is mostly used. Here we will be seeing what is Verilog. Verilog is an HDL language which is used for verifying logic. Use different HDL models. It can be written in any styles as we are seen in the abstraction level, switch level, data flow, gate level, behavioral. It can be done in any modeling styles. RTL code is applied for simulation. Here the term simulation refers to process of verifying the functionality of the design by running its HDL model on a computer software called simulator called simulation. Here it is an example for MUX. MUX we have taken 2:4:1. Data, we have inputs A, B, output Y. The selection line is named as S. It is a basic module types. Input is given as A, B, S, output is Y, assign. Here it is an data flow modeling. We will be using this conditional operator question mark. And finally we have to end the module. Synthesis. Process of converting an RTL design into an optimized gate level netlist. This is performed by a computer software program called synthesis tool. The synthesis tool can be Xilinx, Metagraphics, Cadence, Synopsys, ICC2. Here we have given a basic example A, B, S as a selection line, as we are considering a program for MUX. So the module name is MUX 2:1 data Y A B S. Input AB, output Y. S is also considered as a input. Input A, B, S and output is Y. We are using a data flow modeling style. So we are using an assign Y is equal to S question mark A is to B colon. And here the module should not give a space. So we are ending the module with an end module. The netlist. Netlist is nothing but again the interconnections and gates what we are using. Here is the verilog module. Module is nothing but the name what we are using and the structure. Here we have a design behavior, data flow, input stimuli, clock generation, instantiation of DUV, design under test. Here is the very first module of a design. The module hardware description in verilog should be connected in special construct called a module. The syntax for module is as follow. Module name, for example, we have considered MUX 2:1 MUX, and input, output port and the function of the port is to be assigned, and finally it is end module. Example, we have considered a MUX. It is an model of an individual design unit. As like that we can construct MUX, full adder, encoder, decoder. Structure of design module. Verilog module consists of three parts. Port declaration used to communicate with other modules. Variable declaration, functional verification. Port declaration is nothing but input ports, output port. Here for MUX we have input port A, B and another input is S and output port is Y. Variables. Here A, B is considered as an input variable. S is also considered as a selection line input and Y is considered as an output. Here the functional verification is in order to selection the line. Modules cannot be nested. So here it is a function example of a port. Declaration, variable declaration followed by functional description and module. The ports are required to communicate and exchange data between verilog module and external environment because input and outputs are mandatory for any communication. There are three types of ports in verilog. Input ports, which is declared as input, output port, which is used to transfer data, and the keyword used is output. There is another data in-out, bidirectional input output port. All these by default behaves like variable type wire. Input output ports can only be of type wire. Data types. It is called data types. Wires are used for interconnection. Output ports can be made by the type reg. Reg is used for storing data. Again, there is an example of a design module ports 2:1 MUX. Input ports A, B, S, port and variable declaration, output Y, functional description. Again, it is a functional description. For example, assign statement is used for data flow modeling. And another one is procedural block, always block, initial, which is used in behavioral modeling. These are constructs used to describe the functionality of a design in a verilog model. These constructs execute concurrently with each other. Example, input output ports, which is given by the equation input A, B, S. The port module name is MUX. Inside that bracket, output Y is declared A, B, S. A and B, S are inputs. So inputs are A, B, S, ports and variable declaration. Output is Y. Here we will be using assigned data flow modeling style, structural style. Y is equal to S question mark, B is to A. Functional description. This question mark is an operator. B and A are operators. Operands. So the question mark is an conditional operators. following by we have to end the module. Thus y is equal to s question mark b is to a comes under operators data flow modeling style. S is a selection line, the question mark is a syntax. We have to use for conditional operators. Again we have to have a test bench in order to test our inputs. Design under verification under test bench. We will be giving our inputs and finding the output as per the functionality or not. The verilog model consists of three parts: port declaration, variable declaration, design model instantiation, stimuli generation, input clock generation. So these instantiation is nothing but copying of design. What the design we are using as to function as per the logicals. Port declaration, variable declaration, design model instantiation, stimulus. Stimulus is nothing but the inputs what we are giving. There are two types of ports in verilog. Input port, which declared in design as an input declared as a reg for storing. Output port declared as wire in test bench. The module mux is used here for testing, so it is used for TB, reg, TB, wire, YTB. This is a design module instantiation, stimulus generation, and we will be checking our input stimulus. This is the structure of the test bench module. Design module instantiation is nothing but a copy of a design. As per the module is functioning as per the original module. The values are passed into the design module through their ports. This is the example. Design under verification test bench are used to verify our design. Here we will be using generate stimulus generation, procedural block, always block, initial block. This is the program for test bench TB. Reg and wires are used in test bench generation. Thank you all. Here we will be giving stimulus input 00, 01, 10, 11. This is the stimulus generation initial begins.